Welcome back, my lovely students. We are now going to deal with mixtures. These get quotes because many of the word problems that are associated with this are dangerous. They didn't ask a scientist, is this a good problem? Because the scientist would have said no. It's constantly missing two different concentrations of the same compound. You don't do that in chemistry. If I got 1 molar hydrochloric and I want to make 10th molar, or if I want to make like 0.5 molar, I don't mix 10th molar and 1 molar, I mix 1 molar and water. So also, due to the way chemical compounds work, the mixing is not proportionate the way this implies. So when you read these problems, take them with a grain of salt and realize it has nothing to do with chemistry. This is not the way the calculation would go in chemistry at all. I apologize. Hopefully someday we'll get to talk about science stuff more. What we do have though, and I want you to consider instead, another way we can see this is if we're doing something like making trail mix. So my trail mix, I can have different percentages of kinds of nuts, and the nuts can have different prices associated with them. So if I had like 1 pound of cashews and 3 pounds of peanuts and 2 pounds of pecans, because I live in Texas and they're kind of cheap, and I knew the price per pound, then I could add all those up and then figure out my total cost for that 6 pounds of nuts. And there it does add. So there's the grain of salt. Here's the overall idea though. So when I mix 1 pound of peanuts in with 5 other pounds of stuff, or whichever nut, I have now 1 out of 6 total parts. I could figure out the percentage that is, or the concentration out of the total. So the chemical mixtures they talk about, they're thinking about that in the same kind of way. So down here, we're talking about antifreeze. And I picked this one because it was really weird. So just in case this pops up in Alex, which I'm really hoping it doesn't, but just in case. So like 50% antifreeze, the idea is if I have like a liter of it, half of it is assumed to be 100% pure antifreeze. Like if I could force all the antifreeze to the bottom, then I'd have half of it is pure antifreeze and the other half is other stuff with no antifreeze. So that's the idea with these percentages that are supposed to be concentrations. They're not like the percentages that sometimes show up in chemistry. Like, don't connect those dots. This is in math land, not science land. So here, let's see. Description. One car manufacturer recommends a mixture of 65% antifreeze be used. How much 50% antifreeze solution should be drained from a 4-gallon tank and replaced with pure antifreeze to produce a 65% antifreeze mixture? So antifreeze is a pain to deal with. You don't want to leave it out. It smells sweet to dogs, cats, and small children, and if they eat it, die. So disposal of antifreeze, very important. You do not dump it down the drain. You do not dump it down the sewer. You have to collect it and turn it in. Usually to one of the waste management places, and it's a pain. Which is why we pay other people to change antifreeze. But for this particular person, we got this 4-gallon tank. So there's our total amount of liquid. And right now it's full of 50%. So we're going to assume the antifreeze itself doesn't actually settle, that the whole thing is always 50%. So if I pull 1 liter out, that liter is 50% antifreeze. And then if I pour 1 liter of pure antifreeze in, now I've raised the concentration to some different number, which we could figure out and calculate. And that's what we're going to take a look at. So anytime we have that pure, the assumption is that's 100% pure when we're looking for the number. Now, when I take my concentration and the volume of that liquid I have and multiply those two, I get the amount of pure compound needed or within that particular set. All right, so we've got the things we're mixing and the end result. So I'm going to call it mix 1, mix 2, and what we want at the end. So at the end, I want to see 65% antifreeze. So I'm going to put that there. What I have to mix is 50% and 100%. So just like gut check, if I mixed equal amounts of 50 and 100% in Mathland, that would give me a 75% solution. If I mixed more 50% and less 100 pure, I'd get a number, a concentration that's closer to the 50. So our gut check here is, since 65 is closer to 50 than it is to 100, we should have more 50 in the tank, and we're going to mix in a smaller amount than what will be in the tank to get it up to the 65. All right, so we have our compounds. Now here the volume is really odd. So the 50% is right now the entire 4-gallon tank, but we're going to take some out and replace that with the pure. I don't know how much though, so that unknown amount, there's our variable, that X. So the 50%, since we're taking that unknown out, is going to be the 4 gallons minus X. And then the end result, we want 65% and we want the whole tank full. So we want 4 gallons at the end. And nicely, 4 minus X plus X equals 4. So it actually does total out correctly. Now, percentages don't add like that. That's why we need this extra step in here to get to what the amount of the pure stuff is. Because if I can figure out here, if I want 65% of 4 gallons to be pure, I can actually multiply those and figure out the actual volume amount of pure that I want in the full 4 gallons. In fact, let's go ahead and crunch that right now. But remember, percents use the decimal. So 0.65 times 4 is 2.6. Just using our same formula here. So 2.6 gallons out of the 4 gallons needs to be 100% pure. So if I mix 2.6 gallons of 100% pure and the rest of it as 0% pure, which I don't know if that's actually water for antifreeze, but then I would get the concentration I want. But instead, I've got this 50% in there. The same calculation we did applies, though. We're going to do 50% times 4 minus X. Again, the decimal, though. 0.50, or you can write 0.5 times 4 minus X. And then down here, 100%, if I move it over, is 1. So I'm going to write it as 1.00 for a second, just so you can like kind of remember why we have that. But then it's going to go away because 1 times X is X. Now these amounts, that 2.6 gallons is like fixed. That is how much pure I want to see. Right now, I've only got 2 because 50% of 4 is 2. I've got 2 gallons. So essentially what I'm going to do, and we're going to see this show up in the calculation, is I've got to add however much volume would make this equal 0.6 gallons of, well, I think it would actually be 0.6 gallons then. All right. But these guys are all going to total. First plus second equals end. So 0.50 times 4 minus X plus, all right, the 1, just so we remember where it's coming from, is going to equal 2.6. Now we distribute 0.50 times 4 is that 2 I was just talking about, 2 gallons, minus 0.50x Still plus an x. You can write 1x even, that's fine. All right, we got some like terms in here. We'll go ahead and take care of those. So 1 whole minus 0.50 would be the other 0.50 to get a whole. So a half and a half makes a whole. Or if we think about the percentages, like 100 minus 50 would be 50, but as the decimal is 0.50. But it's going to be positive 0.50. And we still have that 2 in front and the 2.6, which now I will move that. And now we can minus the 2, minus the 2. 0.50x now equals 0.6. And then to get x by itself, I divide by 0.50. Now I know that's really a half and I can multiply by 2, but I am lazy because I'm just going to type this on the calculator. Because I don't want to stress about it. I have the calculator, so I'm going to use the calculator. My parents did not have calculators and didn't get to use them, so I kind of consider it like a personal responsibility to use the calculator. So there we go, 0.6 divided by 0.50 equals 1.2. Ooh. 1.2. All right, we got a number. 1.2 what? This is part of that translate your answer, figure out what it means. So zoom out, rewind back to the start of the problem. I put X next to the 100%. That's in the spot for the volume. So this 1.2 is a volume measure, which for our particular problem is gallons. So this is 1.2 gallons of, similar to our bank account problem, we're going to label it with the percentage. In this case, 100% pure. So how much 50% should be drained and replaced with pure? 1.2 gallons. Because it's removing some of the pure when we pull out the 50%. So we have to add back in to compensate for that. So that's why we ended up with double the 0.6 that I was originally kind of common sensing to. Alrighty. So we'd be mixing 1.2 gallons of pure and then the other 2.8 of 50%. And we can check that calculation. So that was, oops, 1.2 times 1.00 plus 2.8 times 0.50. And then, it's because my video's mirrored. I don't know if you guys can see, but it does show the answer of 2.6. And 2.6 is indeed the amount of pure that we would need to get the 65%. If I take that and divide it by the 4, whoops, not like that. Have to hit equals first. And divide it by the 4, I get that 65%. So I do like to try to emphasize that when we have a word problem, these numbers do mean something. It can be a little weird to try to hold all of that in your head at once. So like have it in there when you're figuring out what equation do I want, where do I get it from? Then you can kind of just crunch the numbers and then at the end go back. What did this number mean? All right, stop this one.